Okie dokie. Find the area contained between curves. So, unsurprisingly, you get two curves, and you find the area between them. That's not the end of the lesson, unfortunately. Alright. So, I've got these two things. What do they look like?
Right.
Beautiful. And I'm going to fix that because that's nowhere near 45-ish. I'm not impressed. I don't want it there. Oh, actually, the first one was probably better anyway. So just really do it again. No, first one actually wasn't what I was thinking around the wrong way. Good job, mate. Alright. Are there any significant points?
Yes.
0, 0, 0.
And 1, 1, 4.
And 1, 1. Cool. Beautiful. Okay. If I ask you the area between the curves, what am I asking about? What's
Probably that little bit in between the like.
a little bit between the curves?
Yeah.
Pretty much, yeah. Funny that.
Yeah.
Cool. So we want that bit.
Yeah.
Cool. Is there an obvious way to get this straight away?
Yes.
Okay, what's that?
Integrate 4 between 0 and 1 for both, and then subtract
Oh, sure.
the parabolas one from the straight line.
Okay.
Yeah.
So if we think actually, I'm going to change this out for the pig because that's how we read. I think it's green. Okay, so we said let's go look. So the integral of which, and then so the integral of x dx from 0 and 1 minus integral of x squared from 0 to 1 equals, what do you want to call this? Capital A for area or whatever, right? Beautiful, cool. Is that relatively easy to think about and be done with?
Yeah.
Yeah, is everyone happy? Yeah, beautiful. Okay. We're going to have that same basic idea for a couple of things. I'm now going to ask this annoying question. If I now draw that, right, what changes on the graph? Right. Because I've already drawn the graph, I'm going to just move the axis instead.
Yeah. Are you now asking for the same between the curves or
2 seconds, so this is now 0, negative a half, this is now 1 half. Cool, we happy about that?
Yeah.
Okay. Does this method now still work?
Yes, but not in the same way.
Yes, but not in the same way.
Like
Okay.
you can still use a similar method, but you just have to.
Okay, you can use a similar method. Okay, can I use the same method?
No, not like this. No.
Okay. So, what method do you want to use this time?
Maybe label different areas that we can actually.
Okay, so we need some more labeling this
Yeah.
time? Okay, fine.
Is
So,
that trying?
where these are maybe, or?
Yeah.
Yeah? Okay, well this one's going to be at half 0. This one's a little bit more annoying. Where's that going to be?
It's root. Half percent.
root of a half, right? So root a half, or in other words, 1 on root 2, or in other words, root 2 on 2.
Yeah.
Yeah? Right, the minus of the OU. Yeah, so we got this one. Cool, okay. Well, looks like we're getting a bit more complicated with our areas. Yeah.
Are those triangles similar?
Are those triangles similar? What? Sorry, which triangles are you talking about?
From
The-
1/2.
Oh, yeah, you're talking about for the x minus.
Oh, this one and this one?
Yes.
Yes.
No,
Because they've got the same angle in the top, so.
Use that for-
I'm not sure how you would,
the
because
triangle from 0 to half, can you use that similar from the triangle from half to 1, isn't it? It's just like negative.
so that area, the triangle from
0 to half, but only like equals x minus a half.
so 0 to half this one.
No, the triangle, yeah, but on that inside the, like if you integrate what
The
you
one
get.
that touches the origin.
One, yeah,
Oh, this little the empty
Yeah.
one. Sorry, yeah.
yeah.
What about it?
Isn't that similar? That's the same area.
This is the same area as this.
Yeah.
Yeah, but we don't want all of this. We just want the green bits.
Yeah, but can't you use that to?
Oh, could we exploit that somehow?
Yeah. We could-
Not sure how you can do that.
Wouldn't you find the area under the curve of the x squared and then minus that triangle? It's not
Area under the x squared. So wait, when you say the area under the x squared,
Yeah.
are you talking about the red?
No,
But I'm not sure.
I'm talking about like the green plus the triangle.
This green plus this empty triangle. Okay, let's. So
Maybe it's
green.
Like, isn't that what it will tell us?
Yeah, let's go green.
No, but what just tell us that you like the
Okay. Can you now tell me what colours you're talking about?
Yeah, I think so.
Go.
Blue, like the blue plus the green.
Yeah.
That's just, when you solve for integration for the x squared, or is that not right?
Okay, so we're going to get the integral for x squared between, sorry, x squared minus half.
Between, like, what is it, 0
0
and 2 and 3, 2 and 2.
So is going to equal blue plus green.
Yeah, and then can't you subtract blue?
Yep, which we know is blue equals, what's that, half by a half by a half. Yep,
Yeah.
almost anyway. There's a slight problem with that.
What divided is probably.
It's a negative area, we get this underneath.
Oh, yeah, so you're for absolute with blue, right?
Right, so we could do that and then absolute. And take absolute of all this as well. Okay. And then we still need purple, red. How are you going to get that?
You could do the area, oh, you could do blue minus, yeah, blue minus the area under the curve for the red.
Right. I'm going to call that bit. Change this to pink. Oh, because I've got all of red now. Blue is this plus pink. There we go. Is that right? Yep. And then pink is integral between root 2 on 2, 1. We don't need an absolute, that's fine. Under x squared minus a half. Yes. Equals pink. Good. Okay. Fine. Okay. If we go back a step, remembering that this original blue, sorry, that's just that, that's that, so this was the original area that we wanted, which is plus area of purple. Okay, let's solve this. Ooh. Area contained by that. Alright, integral, so we've got half x squared between 0 and 1. 0 is going to cancel to nothing, 1 is going to square, this is going to be a half. Minus all of this thing, 1/3 x cubed between 0 and 1. That's going to go to nothing, that's just going to be a third, so we get minus 1/3 equals 1/6. Right, so that's green and purple together.
Yeah.
Beautiful. Oh. Alright, let's solve this guy. So, did we end up structuring an answer? No, okay. So we've got this is blue plus green, and we know blue equals 1/8. So we want this thing. Is that right? Yep. Minus that thing minus blue, which is 1/8. So that gives me just green, and then to get purple, we want blue minus pink. So plus 1/8 minus all of this, root 2 on 2, 1, x squared minus a half, dx. Okay.
Doesn't the 1/8 just cancel out?
Doesn't the 1/8 these?
Yeah.
Yeah. Okay. Are we happy that that's satisfied? Yep. Okay, beautiful. So now we've got okay.
Yeah.
What do you want to do from there?
Solve.
You want to integrate from there?
Yeah.
Okay, we'll integrate that. Integral this is 1/3 x cubed minus 1/2 x between 0 and root 2 on 2. That's going to go to nothing. Yuck. So we've got what? 1/3 by root 2 on 2 cubed minus root 2 on 4. That's all that. Say anything. One's into this is going to be 1/3 minus a half minus 1/3 root 2 on 2 cubed minus root 2 on 4. Cool. We're happy about that. Alright. Has anyone noticed a much shorter way yet? No? Okay. There's a whole bunch of shortcuts we could have taken, but fine. You know, we can do all the work. Alright, so we've got this. We can turn this into 2 to the 3, so this becomes 8, so that becomes 2 root 2. So we've got 2 root 2 over 6 minus root 2 on 4. This is going to be 1/6 in here, so minus 1/6 because of that. Oh wait, sorry, no, positive 1/6 because of that. Oh, maybe I should leave this in several steps just to make it clear what's going on. So this is negative 1/6 of that minus same thing here. We've got 6 down here. This is 2 root 2 with a minus in front. Minus becomes plus. Root 2 on 4. Have we got that all right? Probably not. It's messy. That goes, that was not, this goes, this. No, I think I've got a negative error somewhere. Negative, this should be negative. Negative, this should be positive. Negative, this is already negative, this becomes positive. Oh wait, I've still got this negative here, that's why. So this is currently negative 6, yes. This is positive. This is negative. What What should this have been? Plus originally. Flat in there. Is this so blue minus pink? Blue minus pink, yes. That's right. That's right. Is negative 1/6, yes. Yes. Is negative, it should be negative. Oh, it is, yeah, that makes sense. No, but this should be negative. Yeah, sounds right. What's going on? Oh, there's some mundane negative error in here somewhere. There. What should end up happening is we'll get 2 root 2 on 6 minus root 2 on 4 plus 1/6 minus 2 root 2 on 6 plus root 2 on 4. That's where it should have ended up. Those guys cancel. Those guys cancel. We end up with 1/6. Blah, blah, blah. It's the exact same.
And this is good.
Yep.
Could you take out x squared minus half? No, very.
So I've got x squared minus half. What about it?
From the line below that, could you factor out x squared minus half?
From this line
From the line below that,
below. Yep. Can you
factor out x squared minus half?
factor out x squared minus half? They're both trapped in integrals. But what you can do
So you can put one in.
is say, I want, oops, for a second. Both my integrals relating to that statement. Right, okay, this one goes from 0 to root 2 on 2. This one goes from root 2 on 2 to 1. Right? If I was adding these, then I could have just put them all in one integral. They're not adding. But if I consider what's happening at these things, I go root 2 on 2. Okay, one of them is taking this area, which is a negative area. So this number should have ended up as negative, which I don't know. Never know. Yep. This one should have ended up as negative. This one should end up as positive. Since I'm minusing this, wait, is that what went wrong? Don't know. Yeah, since one of these areas is negative and one of them is positive, if I add them, so if I go from 0 to 1, then I'll end up with the area anyway. And that's not necessarily straightforward thinking, but let's just do that. Then on the side, unless I drop the negative in there, and the whole thing should be negative, we'll find out. I don't think so. 0 to 1, 0 is going to disappear. Oops. Sorry. 0 to 1. That's going to disappear. So what do we get? 1/3 minus the half. I don't have to drop a negative, the whole thing. We want the absolute value of this. Solutions. Do that backwards before. Ah, that's what happened. We wanted the absolute value of this guy. That's why. Because this was a negative area. So we wanted the absolute of this, the absolute of this, the absolute of this, absolute of this. Which is equivalent to that. I think that's going the right way now. Yeah. Anyway, so was this irritating and complicated?
Yeah.
Yes. Did we end up back at the same spot?
Yeah.
Yeah. Why did that happen?
You didn't change the shape.
Because I didn't change what?
The shape.
The shape, right? It's the same geometry. Yeah? It's just you've got this arbitrary constant that constant doesn't change the area. Because if you think about it, this was, you can consider this a negative area if you want, but that means they've both got negative areas, so their difference just becomes that area anyway. Yeah? So the good news is, if you have some curve and you want the area between the curves, you can totally ignore where the x-axis is. Okay? It doesn't matter if it's there, there, or there, the area between them will be the same. So you can treat it as though the x-axis is down there, just so that your brain goes, yeah, no, it's all a positive area, that's fine.
So you do the same thing as the first one.
Yes. Okay? Do you want to do that? No. Right? So the only reason I do that is to show, hey, you should end up at the same spot anyway. Right? But obviously, that's a lot more work. So if you can just set out something simple, do the simple thing. That's great. Okay, something a little less straightforward. Cool. The area between sine of x and cos of x, and we're only looking between x is 0 and 2 pi. We'll use those as boundaries though. So what's the first thing you're going to do? Right, do a picture. Right. Okay. Sine. Something like that. Cool. Alright. We've had 0 and 2 pi. So let's give these some names. We'll go green, blue, purple, red. Okay. So that's the area we want. Is this going to be obvious and straightforward? No? Okay. I'm asking you.
It probably is straightforward, but you've got to
With a bit of experience, it's definitely, there's some smart things to do, but that's fine. Okay. Is there anything else we should probably put on this to help ourselves? Points? Okay. Which points?
0, 1, 2.
So we've got 0, 0, 0, 1. What else?
Pi 2.
Pi on 2.
Pi.
Pi on 2, 0, pi.
Points of intersection. 2 pi.
Okay. Points of intersection, where's that? That numerically, where is it?
Pi on 4.
Pi on 4. Where? Pi on 4. Root 2 on 2. Anywhere else? So you get 3 what? 3 pi on 2, I've already got.
5
5 pi on 4, that's what we're looking for. Cool.
And then 2 pi.
Go. Are we happy? Yes. Okay. Which area do you want to do first? First one? Okay. What's the first one? Because whichever one we do first will be the first one. Okay, great. Cool. All right, so let's figure out green area. How do I get green area?
You take the equals of both and minus 1 from the other. Like
Okay.
the disposal.
Which
You
one?
integrate sine and cos between 0 and pi.
Okay, so between 0 and pi and 4 is good.
Oh, sorry.
What do I write in here?
Huh?
What do I write in here?
Sin x dx. Oh, it's cos minus sin.
There we go. Good, good. Right, why are you doing cos first?
Because cos is the larger area.
Right, cos is on top.
Yeah.
Yeah. So cool, so we want cos minus sine Now, could I split this into two separate integrals?
Yes.
Yeah, right, you can do cos of x dx between these minus sine of x between these, or you can just do it in one integral. Makes no difference.
Do you need, is that the same with everything, or just?
So long as they've got the same interval, yeah.
Yeah.
But it's up to you. Like,
So
you could do this as one integral, or you could do it as two. Makes no difference.
Oh.
Right. Most of the time, I would probably recommend do it as one, just because then there's less ways that you can stuff up. And if you've got a minus here, then you have to remember you're minusing that whole set of brackets.
So on the one on the left, you could just integrate x minus x squared and get the same answer. And you get this, and okay.
Right? Math needs it easier, yeah? And this is why you want to know all these ways to fiddle with integrals, because it's not so that we can give you more annoying things to fiddle with, it's so that the annoying things that you're going to get, you can make them easier. More tools in the tool belt. Alright, cool. So we've got this guy, great. If we integrate, what do we get? Plus cos?
Doesn't cost anything, it's
Oh, it's you guys.
Maybe some.
Are we okay with this or not?
Yeah.
Yeah, alright. Easiest way to check, derive it instead. Sine goes to cos. Cos goes to negative sine.
Oh, yeah.
Right? Always just do a quick derivative because it's easier to derive than integrate almost always. Beautiful. Okay. Cool. Can I just cross out the zero? No. Why?
Zero.
Right. They're not all zero at that zero. Okay. Fine. Sine of pi on 4. Cos of pi on 4. Cos of 0. Cos of 0. Cool. So we've got root 2 minus 1 is my green area. Yep.
Yep.
What do you want to do next? Blue? Okay. Okay, how are you going to get blue?
Would it be easy to look at the,
Say again.
wouldn't it be bad to look at the,
Wouldn't it be better to work out purple? Okay, why do you want to do purple?
because then you can add it to, green.
Okay. So, purple. Alright, what are you doing?
Integral from 3 pi to 2 pi.
Okay.
No, sorry. 3 pi on 2 to 2 pi.
Yep.
That's what it
No, so-
Cool. Alright. What am I writing in the integral? Cool. Cos minus sine.
Yeah. But that will get you the other little area a little bit as well. Oh, that's only double it, so you can just divide by 2 again. So the whole thing will work.
Okay. We're beginning to think about symmetries, which is good.
Yeah.
So-
So you're gonna have to divide the whole thing by 2 just to get purple.
Is that actually double?
Okay. We'll hold up. Just back up a second. Are we happy that this represents purple?
No.
No? Okay, what's wrong with it?
Because it also represents the other little bit underneath, doesn't it? And that,
Does that down here as well?
yeah.
Okay. So, we need
So you need to take an absolute value and then.
plus, I'll say P.
Yeah.
Okay?
But
So
that's a-
P isn't all of pink, it's just this bit.
Yeah, but that's a negative area though, so when you integrate it, it's like,
Okay, so think about what you're doing. You're taking this thing, minusing this one,
yeah,
right? This bit's a minus, so if I minus the negative, I'll end up adding it.
yeah.
Remember, the x-axis, you can imagine it just being down here, and it'll
Yeah.
still give you the area between it. But it's good that you're thinking like that, because you should like have a little bit of a nervous trepidation going, hang on, this is a negative area, and if I'm doing that, isn't this going to add up to 0 instead?
Yeah, but
Right?
it's,
But it turns out, no, the negatives take care of themselves. Okay, so we've got this, great. That's those two. If I just want purple, what should I do?
Minus
B.
Minus B?
Minus P.
Minus P, okay.
But it's the same as divided by 2, isn't it?
Right, it'll be the same. Is everyone happy that purple plus this bit are going to be equal? Yeah, so to get this times by half.
Yeah.
Cool. Sylvia's okay? Yep. Okay. Cool. Well, no, we haven't integrated this. Oh, yes, we have. Yes, we've integrated this before. Beautiful. So half. Lots of this. So it doesn't take that long anyway. Between 3.2 and 2. Cool. Yeah, okay. Sine 2 pi plus cos 2 pi.
Oh, yeah, okay, I see what you're, okay, I see what you're saying. That's, yeah.
All good? Yep. Sine 3 pi and 2.
Wait, Adam,
That's fine, we see it.
Adam, did you finally see it?
No.
See?
Yep.
No?
Plus cos 3 pi and 2.
0.
What is what? It depends what you're looking for. You said, I see, what am I seeing?
Lots of 1 plus
Blue is
1.
equal to red is equal to pink is equal to green plus purple.
Yeah,
Cool.
that's what we're talking about.
Yes, that's why I'm asking you to see it yet.
Yeah, okay, cool.
All good?
Yeah.
So we end up with purple is exactly 1.
Yeah.
Is that a bit surprising?
No,
Why?
I don't know. It's definitely not surprising.
You end up with this shape. Is it odd that that's exactly 1?
Would it be more than one?
Why?
I don't know. But it's, oh yeah, actually no, true.
Right, you've got this weird curved area, but it's exactly 1. So it's surprising that, oh, it's a nice curved area that's exactly 1. You'd expect there to be a pi or something in
like
there.
a unit circle or something. Like
Right, we're dealing with sine and cos, right? So then it's like, oh, it's a curved area, that's weird that it's 1, but then when you think about, oh, hang on, it's got sine and cos in there, it's all based on a unit circle, so maybe it's not so weird that that turns out to be a perfect 1. Yep.
Can we now add green to purple and time to by 4?
Okay, so, next curve.